Unit 3, Section 5, Ratio Test. Session objectives. By the end of this session, the students will be able to 1. State the ratio test. 2. Use the ratio test to check the convergence of a given series. Meaning of series: divergent and convergent series. Series is obtained when we add the terms in a given sequence. So meaning if a sequence is given and we add the terms in the sequence, then we have what is called series. For instance, if a sequence is given as 1, 3, 5, 7 up to infinity, then for us to obtain series from the given sequence, we write 1 plus 3 plus 5 plus 7. Then because we are connecting the terms with the addition sign, we have what we call series. Now series may be finite or infinite depending on the given sequence. Now we want to look at how the series behave if we are summing from n equals 1 up to infinity of, let's say, x sub n. Then the ratio test may be used to determine whether the series diverges, whether it converges, or whether we cannot draw any conclusion about it. Now we are taking the limit n approaches infinity of absolute of x subscript n plus 1 divided by x subscript n. Now to see how this series behave, we find the limit of this series. If after finding the limit, and the limit is greater than 1, then we conclude that the series diverges. However, if after finding the limit to infinity of this series and it is less than 1, then we conclude that the series converges. However, after finding the limit, if the limit gives 1, then in that case, we cannot draw any conclusion. The ratio test. If a series is summing from n is equal to 1 to infinity of x subscript n, where x subscript n is not equal to 0, is such that when we find the limit as x is approaching infinity of the ratio, the absolute x subscript n plus 1 over the absolute x subscript n is equal to L. Then we say A, the series converges absolutely if L is less than 1. B, the series diverges if L is greater than 1. And C, if L is equal to 1, the test fails, so we cannot draw any conclusion. Using the ratio test to determine whether or not series converges or diverges. Example, determine if the following series is convergent or divergent. And the series is the summation from n is equal to 1 to infinity, then into braces negative 10 exponent n divided by 2 exponent 2n plus 1, then raises n plus 1. Now, to determine whether or not the series is convergent or divergent, then we have to find x subscript n plus 1 from the original x subscript n given. What it means is that wherever there is n, we increase it by 1, so that our x subscript n plus 1 is equal to into braces negative 10 exponent n plus 1. It is n plus 1 because the original x subscript n is 10 exponent n, or negative 10 exponent n. So we increase the n by 1, divided by 4 exponent 2 into bracket n plus 1. The bracket closed, then plus 1. Now, if 2 into bracket n plus 1 is expanded, that gives 2n plus 2, then plus 1, which gives 4 exponent 2n plus 3, then into raises n plus 2. But we know our limit L is equal to the limit n is approaching infinity, the absolute of x subscript n plus 1 divided by the absolute x subscript n. Now we have obtained our x subscript n. Then we now divide x subscript n plus 1 by x subscript n. So therefore, the limit is equal to the limit into raises negative 10 exponent n plus 1 divided by 4 exponent 2n plus 3 into raises n plus 2. We know when we are dividing, we reciprocate the denominator and change the division sign to multiplication sign. Hence, we have 2 exponent 2n plus 1 into raises n plus 1 divided by negative 10 exponent n, which is now multiplying the x subscript n plus 1. We continue in the next slide. From our previous slide, we simplified using indices, which implies our negative 10 exponent n plus 1 can be written as negative 10 exponent n times negative 10 exponent 1. Also, in the denominator, our 4 exponent 2n plus 3 can be written as 4 exponent 2n times 4 exponent 3, then into raises n plus 2. All this term multiplying 4 exponent 2n plus 1, which can be written as 4 exponent 2n times 4 exponent 1. Another raises n plus 1, all over negative 10 exponent n. Now simplifying further, the negative 10 exponent n cancels out negative 10 exponent n. Also, 4 exponent 2n cancels out 4 exponent 2n. The 4 exponent 1 cancels 4 exponent 3, and we are left with 4 exponent 2. So the whole thing reduces to negative 10 into raises n plus 1 divided by 4 exponent 2 into raises n plus 2. So when we take the limits of the absolute as limits n approaching infinity, absolute negative 10 into n plus 1 over 4 exponent 2 into n plus 2, then this gives 10 over 16, that the limit n is approaching infinity, n plus 1 over n plus 2. And note that a negative 10 over 16 is positive because we are taking the absolute value. Hence, 10 over 16 limit n is approaching infinity, n plus 1 over n plus 2. And if the limit is taken as n is approaching infinity, then n plus 1 over n plus 2 becomes 1. And hence, our limit L is equal to 10 over 16, which is less than 1. Hence, we conclude that the series is a convergent series. Determining whether or not a series is divergent or convergent. Example 2. Determine if the following series is convergent or divergent. And the series is, we are summing n is equal to 1 to infinity of n factorial over 5 exponent n. Now, for us to show that this series is either divergent or convergent, meaning we have to obtain x subscript n plus 1. What it means is that in the original series given, wherever there is n, we increase it by 1. So our x subscript n plus 1 is equal to n plus 1 factorial divided by 5 raised to the power n plus 1. Now, to find the limit L, we have to divide our new series, which is x subscript n plus 1, by the original series x subscript n. So L equals the limit n is approaching infinity, the absolute n plus 1 factorial over 5 exponent n plus 1 divided by n factorial over 5 exponent n. But if we are dividing, we reciprocate the denominator and change the division sign to multiplication. Hence, we have the limit n is approaching infinity absolute into braces n plus 1 factorial over 5 exponent n plus 1, then multiplying 5 exponent n over n factorial. Now, using indices, n plus 1 factorial over 5 exponent n plus 1 can be written as n plus 1 factorial over 5 exponent n times 5 exponent 1. So that 5 exponent n cancels out the 5 exponent n. And we are left with the limit n is approaching infinity, the absolute into braces n plus 1 factorial over 5n factorial. Now we know n plus 1 factorial is n plus 1 multiplying n plus 1 minus 1 multiplying n plus 1 minus 2 into braces factorial, then divided by 5n into braces n minus 1 factorial. This will simplify to n plus 1 over n, taking the limit of that as n is approaching infinity. Now, if the limit is taken, then we have the infinity plus 1 over 5. Any large number divided by small number will give you a large number. Hence, the limit is infinity, which is greater than 1. Hence, we draw the conclusion that the series is divergent. Determining whether or not a series is divergent or convergent. Example 3. Determine if the following series is convergent or divergent. The series is the summation from n is equal to 1 to infinity, 9 exponents n divided by into braces negative 2 exponents n plus 1 multiplying n. Now, to determine whether or not this series is divergent or convergent using the ratio test, it means we have to find x subscript n plus 1, which implies that wherever there is n, we increase it by 1. So this gives x subscript n plus 1 to be equal to 9 exponents n plus 1 divided by into braces negative 2 exponents n plus 2 into braces n plus 1. Now, but we know the ratio test is the limit as n is approaching infinity, the absolute x subscript n plus 1 divided by x subscript n. So that we have the limit L is equal to the lim n is approaching infinity, the absolute 9 exponents n plus 1 divided by into braces negative 2 exponents n plus 2, another braces n plus 1, then divided by 9 exponents n divided by negative 2 exponents n plus 1 multiplying n. But since when we are dividing fractions in the denominator, we reciprocate it and hence changing the sign to multiplication. And that is why we have into braces negative 2 exponent n plus 1 multiplying n over 9 exponent n multiplying x subscript n plus 1. We continue in the next slide. From our previous slide, if we simplify 9 exponents n plus 1 over negative 2 into braces exponent n plus 2, another braces n plus 1 multiplying into braces negative 2 exponents n plus 1 multiplying n over 9 exponents n. Using indices, we can see that our 9 exponents n plus 1 can be written as 9 exponents n times 9 exponents 1. The denominator negative 2 exponent n plus 2 can be written as negative 2 exponents n times negative 2 exponent 2, and multiplying into braces n plus 1. Also, negative 2 exponent n plus 1 can be written as negative 2 exponent n times negative 2 exponent 1, multiplying n divided by 9 exponent n. Now we can see that 9 exponents n cancels out 9 exponents n in the denominator, and negative 2 exponents n also cancels out negative 2 exponents n in the denominator. Likewise, negative 2 exponent 1 cancels out negative 2 exponent 2, and we are left with negative 2 exponent 1 in the denominator. And this reduces to 9n divided by negative 2 into braces multiplying n plus 1, which gives the limit as n is approaching infinity, the absolute 9n divided by into braces negative 2 multiplying another braces n plus 1. Now, since we are dealing with absolute values, the 9 over negative 2, we consider it as positive. So we bring it out and find the limit of n over n plus 1, so which gives 9 over 2 lim n is approaching infinity, the absolute n over n plus 1. Now, finding the limit, if n is replaced by infinity, it means we have infinity over infinity plus 1, which is a very large number divided by a very large number plus 1. Any large number plus 1 will be large. So the limit of that gives 1. And if 1 is used to multiply 9 over 2, we have 9 over 2, which is greater than 1. Hence, we can say that the series is divergent since 9 over 2 is greater than 1.